All right, let's get this going. So welcome everybody to Effective Kubernetes Development, or how to turbocharge your development loop. My name is Philip Lombardi, or you can tweet me at the Big Lombowski on Twitter. I love to get some feedback from people. I'd love to hear what your thoughts on the slides are. If you want to shoot pictures out all during this thing, that'd be great. So today, this talk, I'm going to share a cloud-native workflow that we have been building for 3 years at Datawire IO. It is a 3-year endeavor. This talk will be kind of a journey talk, so I will talk about steps forward, the steps backwards, the steps sideways we have taken, and our twisting journey towards a brighter future. Just a little bit about Datawire IO. We are a dev tooling company. We build dev tools. We don't really have services so much that public consume, but we have products that people use, and we have services that we use internally. I am an internal dev tooling and infrastructure engineer at Datawire. So I basically help the developers work and be more productive. Occasionally I hack on product. When I first started 3 years ago, I definitely worked on the product way more often. These days, I'm mostly concerned with how to make my team much more efficient when working on cloud native software. I am definitely an impatient person, possibly my Italian heritage, possibly the fact I'm from Boston, just an impatient person. If you were thinking Myers-Briggs, I'm definitely a J. And cloud native software makes me frustrated at times. Right now, we are in the infancy of cloud native development. The tools are not there yet. So there's a lot of room for improvement, and I'm really excited to be able to help out and make things better. This is kind of our typical development loop. Everyone in this room is probably familiar with this. I'm going to call this the internal or inner dev loop. It is the thing you start doing the moment you get a product feature request or you get a bug to work on. You start writing code. You build your code. You deploy your code, and then do some kind of poking at the code you just wrote to see if it even works or does what you expected it to do. And you keep repeating this over and over and over. Now, a note, when I say dev test, I do not mean formal tests. I am not talking about unit tests. I am not talking about acceptance tests. I am talking about the tests you do with curl or your web browser to even make sure the thing you thought you wrote even does remotely what you thought it was supposed to do. And so, for many people, this takes different forms, code. Some of us write Go, some of us write Python, some of us write Kotlin. Some of us work in Java or whatever. We all have different forms of building, binaries, Docker images. It can just be packaging up static assets. Deployment is also that thing we do where we have to get the code running somewhere. It can be a form of kubectl apply. It may be something else. Data migrations are part of deploy. And then there is the mythical stuff that we don't really know what that is, but our company says we have to do it because it's part of the deployment phase. And then dev test, that takes many forms, curl, maybe something formal, maybe something not formal. It's also stuff. This all started in 2015 at Datawire. We were not on Kubernetes at that time. If any of you are familiar with Kubernetes going that far back, it wasn't very far along. It was a 1.0 release, basically, the month we started working on this stuff. But we had to bootstrap our back end. We need to ship fast and ship often, as the mantra really is. And so our dev loop was really primitive at the time. It was basically get code off of laptop, get it on the internet somewhere, poke at it, and play with it, and see what we had to add, fix, and stuff. It wasn't a particularly advanced set of tools. It was some shell scripts, some Python, some mostly documented somewhere. It wasn't complicated. And the way we were doing it at the time was building and packaging binaries, and then building virtual machine images. So we weren't even thinking about Docker at this time. Docker was still not quite the thing we were going like it's the future. So we went with something we knew, which was building virtual machine images and then deploying virtual machine images. Deployment, it was a mix of Shell, Terraform, Ansible, various things happening at various points in time, either when you deployed and changed the infrastructure definition or when the VMs came up. And dev test, as it usually is a wild west of options. So we immediately hit problems with this. Basically, after a few months of working with it, you became quite aware that VM images take forever to create. They are a 10-minute endeavor at best. They may take even longer if you have complicated things you have to do on the VM to get them up and started, generate a snapshot, tear them down. If the build fails for whatever reason, you have to start over again. It could be 10 minutes times the number of failures you have, plus the time to trace whatever the failure was. Further, the failures don't often occur in parallel, they occur sequentially. So as you're debugging the thing, you realize, well, I'm actually solving one error, waiting again, solving another error, waiting, think that's the time, it's all done. Nope, third error. So that wasn't great. Developers especially, really hated working with Packer, which is a HashiCorp tool, as part of their developer loop. Now, I'm not trashing on Packer as a bad tool. It's a great tool for operations, and if you have to build virtual machines, it's possibly one of the only tools that does it for you, and it does a really good job. But developers don't want to think about it. They don't want to have to think about building a virtual machine image. So they got really frustrated when they had to start using this tool, and it didn't work for them, or they had to debug it. Finally, the Shell and Terraform and Ansible combination, well, it was built really hastily. It was janky, wasn't perfect, and caused lots of frustrating problems for people. So what did we do? Well, my first thing was ignore all the speed complaints naively and go and slap a fresh coat of paint on all this by hiding the complicated bits behind makefiles and Gradle scripts. And I was basically of the opinion, great, everything's awesome, mission accomplished, we're gonna move on, get on with our lives. And the reaction from my CTO and my coworkers was, this is a disaster. And they're screaming and yelling, not really screaming and like screaming at me, but they're screaming at their computer screens going, why is this thing still not working? Why is it still a pain? And I'm going, everything is fine. We hit all the complexity. I know how the complexity works, but you don't, and it's fine. So my first lesson here was, don't ignore my developers. I need to listen and understand their problems much, much better before we start actually solutioneering. But this creates two new problems. One, our devs do not always know what their problems are in the first place. And then, even when we listen to our developers and we even sit down and agree with them about what needs to be solved, we fix the wrong problem. So we got all the greatest minds of the company together and decided deployment was actually the first problem we were going to tackle. It tends to be the case that people, engineers especially, we look at a problem, we go, the janky thing, the thing that's got crufty areas or dark areas, that's the thing we should fix first. That's the thing we want to fix. It's not sexy. We want to work on something that's sexy. So we went off and worked on deploy. And we automated the workflow, built fancy custom tools to get around that. The fancy custom tool worked. We built this thing called Swaptop, did all this fancy orchestration stuff, did blue-green deployments for folks. It solved some pain, but it also created lots of pain and new pain, and still didn't address the real pain that developers were actually having at the company. So we, as smart people, as engineers, sat down and went, well, we can fix this. And so we doubled down on deployment as the problem, threw more technology at it, Spinnaker, Jenkins, Terraform, Ansible, EC2, another cloud, Google, OpenVPN. I can name probably 20 technologies that were involved in what we were going to call the Datawire backend developer platform. And at the end of the day, it still wasn't enough. The expected outcome was this. Everyone's going to be dancing. We're all going to be going, this is great. We're shipping code, shipping faster. Going to get the product out there. And this is actually my reaction from my coworker who has long hair going, what have you created? You've created this horrifying disaster. So lesson 2.0. Thankfully, my bosses are really patient people who are interested in getting to an actually good outcome versus just continuing to struggle. So we learned we need to do a better job identifying the real pain, the actual problems that people are having. Don't get too technology crazy. I know this is a really kind of an ironic statement as we sit here at this conference, going with both the vendors, looking at all these fancy tools, going, hey, I should use this, I should throw this in my problem. Try to actually, dial that in. Don't just start throwing technology at your problem. It's probably not going to solve it. So solution 3.0 is the scrap it all and restart from scratch. And we were very fortunate at the time that the business was changing a little bit, so we were given some time to basically sit down, reevaluate where things were slow, and change them, make them better, do the actual right thing, the thing we forgot to do in the first place. So what we finally came to the conclusion was the inability to build quickly was killing us more than deployment. We had all kind of come from a world where writing software was basically a matter of write some code, click a button, or kill a process and restart that. See another server process come up, new code is running. We weren't in that world. We'd started in a world with virtual machine images that had to be baked and then run, and then we got to a world where we were starting to use Docker a little bit. We weren't in the world we want to be in. So we could get sort of closer. We switched to Docker. That cut down our virtual machine problem. So we no longer had the 10 minutes of waiting for the virtual machine to build. We just had to get Docker images built. That shaved off 30 minutes from the entire process. We left the deploy thing kind of unanswered for a while. So in 2017, early 2017, maybe you could really say late 2016 too, the answer to who was going to win the container orchestration problem was just not answered at all. There was Swarm, Kubernetes, Mesos, Nomad. It was an open game. So we kind of just held off. We didn't really need to think about it at the time because we were rebooting the business, rebooting the engineering org. Mostly code and to build worked well enough for us. But at some point, Kubernetes did win. It is now really hard to dispute that it is the best platform for running containers at the moment. And everyone has gotten their attention behind it. So we adopted Kubernetes. And the good news here was scrapping all the stuff that we'd done before, moving to Docker, moving to Kubernetes, the rethink, it was a huge success. Devs were happy, velocity increased. If I could have a little chart with a little bar graph going, or the little arrow going all the way up, it's through the roof compared to where we were. But developers, as they are, always come back to you and say, I want more. I want to be faster. And this is not fast enough. We got to the point where we were in around 2 minutes for Docker images to build, which is huge improvement from where we were in types of 10 minutes, 30 minutes for VM images. But what can we do? And at first I was like, this is impossible. You can't be complaining that this thing is still slow. It's pretty fast. 2 minutes even, is just way better. They're like, well, the problem is we're going through this loop faster and faster and faster, so we're actually able to cycle over and over and over. Those 2 minutes really add up, and they were totally right. Compile the code, 30 seconds. Assemble a binary, another 30 seconds. Build your container image, another 30 seconds. Push the container image, another 30 seconds. You quickly end up at 120 seconds, which is a totally not scientific number that I came up and pulled out. And that's where you're. And then you realize it's 120 seconds is optimistic. How many of you are in this room are Java developers? Yeah. You have probably tried building Java apps in the container and realized every time you do it, because you can't cache that Maven repo, you're pulling all those dependencies down again. Python developers, how many times have you had to build a native extension, had to install through apt GCC just so you can rebuild libpq so you can have a Postgres library? All right, so you really realize quickly these just add up. This time it leaks out around you. Also, slow networks. Slow networks will kill you. All those dependencies have to be pulled down, rebuilt every time. Same thing, the images have to be pushed and then redeployed and pulled from somewhere every time. So it's actually 120 seconds times the number of rebuilds you're doing. And it adds up super quick. You can, in a day, if you have a fast enough dev loop, burn an hour. An hour a day, in a week, 5 hours, gone, right away. So we start looking at ways we can optimize our Docker files. That's the simplest solution. Everyone, when we started with Docker, everyone kind of does the naive thing. They throw a bunch of instructions in a Docker file, and they realize there's no optimization around the caching they've come up with because they're rebuilding all the layers every time. So we did the first thing, which is logically reorder the instructions to get the best caching. Great, that shaves some seconds. Next step, multistage builds. That allowed us to start using a base JVM layer that we didn't have to rebuild every time, or a base Python layer that had stuff built in. Great. Small base images should be self-explanatory. We don't want to see multi-gigabyte images floating around, going back and forth between registries. Lots of time you have to push and pull, so we would like to get small base images, so we worked on shrinking things, getting to Alpine, using from scratch where possible, using a minimal Ubuntu where also possible. We carved from basically having 1 gig plus images down to 100 megabyte images. Great. That solves the entire problem of, well, the pushes and pulls are really slow because moving a gig over the internet, even for a Docker image, repeatedly is a pain. But it wasn't enough. It only shaves some seconds, and it's just not enough. Even the fastest builds still get stuck in that sink of time known as registry push, redeploy, and registry pull. It's the chunk of time to deploy stuff. We were like, okay, well, we can still try one last thing. We came up with a new plan, which was a background daemon, which would continually run on developers' computers, and it would rebuild images as they coded. And this worked pretty well in the form of you got a Docker image instantaneously, so you didn't have to even work on the rebuild part. But it generated monstrous sized images, even worse than what we were getting before when we tried to basically shrink things. So we were getting gigabytes, 2 gigabyte, 3 gigabyte, 5 gigabyte images. Really not good. I had a coworker finally go, well, what if we just didn't build and push images at all? What if we could get basically a Kubernetes native development experience where you could code in a way that felt like you were just running on the cluster and the cluster was aware of your code as you worked on it? That's a really good idea. Kind of brilliant. Gets us back to the world where we just click a button or launch a process and we see our code running. We can change it, reload it, whatever. So What if your dev machine ran your code and it just worked the same as if you ran on Kubernetes? We tried a couple approaches with this. One of the approaches we tried was the idea of, we'll just run the kubelet on your laptop, and then we'll join the laptop into your cluster. That turns out to be really not a great idea. One, CNI is a pain to get working across different networks. Two, you have the problem of different developers have different setups for their machines. So I have developers who use Mac OS. I have developers that use Linux, and they might use Fedora, they might use Debian, they might use Arc. It's really kind of a mess to even try and think about doing that. So we came up with this thing called Telepresence. And it's a CNCF project now. It's open source, but what it does is basically has a magical bidirectional proxy that will sit on your computer. And when you have it started, it talks to a pod in Kubernetes, and that will make it so that you can basically bidirectionally communicate with Kubernetes, and Kubernetes can talk to the stuff on your local machine. So suddenly, the dev test loop no longer even really has a deploy phase. It doesn't even really have a build phase where you have to build Docker images. It just has this part where you have to recompile your code, restart your process. And that is an awesome experience. Just to give a little idea of what this looks like, say your foo app, like, well, the square is your local machine. Obviously, the Kubernetes cluster is our septagon over here. You have a proxy agent on it. It's talking to an app on your side. And then you have the Telepresence pod, and that is talking to whatever you want on the Kubernetes cluster. So if you have traffic coming in from a load balancer or a node port into your thing, hits a service represented by kube proxy, that'll get routed into the Telepresence pod, and that will be sent over to your local machine. We also do DNS hijacking, which sounds really scary, but it's actually not, so that when you actually are on your local machine, you can talk to the Kubernetes services as if they were right available to you. So I can talk to barapp.service.cluster.local, and I will get a result. I do not have to change anything. I don't have to rethink how I'm going to connect to it. It's just natively available to me. So it actually killed two birds with one stone. We no longer had to deploy our code, because basically your deployment is now restart the process, and your building is just restarting the process. You have to rebuild your binary or your executable or whatever you're doing, and it just drastically simplifies the entire problem. There's also an awesome secondary benefit here. Your code is on your machine. Think about that again. Your code is on your machine. You can do all the things you do with code that is actually on your machine, which means, for example, a debugger is super easy to set up from your local machine. You can set up breakpoints. You can have traffic coming in through the production Kubernetes cluster, have it routed to your pod, your Telepresence pod, end up on your machine where you can then set breakpoints and see the entire stack of the request. Awesome. We can get out of this world where we're printf debugging. It horrifies me that we have spent decades in this industry building awesome debug tools, and we still resort to basically printf debugging and grepping through logs. It's brutal. So back to our expected outcome. Everyone's going to be dancing. Everything's going to be great. And it actually was, finally. We got to this actual outcome. Everyone's dancing. This is awesome. I can write code. I can basically hit a button or kill a process, restart a process, and we are going to be able to reload my code and use it on the cluster. Right? Mission accomplished. Never. No. Not quite. Devs are never satisfied. You give them an inch, they'll take a mile. And they'll ask not just for a mile, they'll ask for a leap, a giant leap. Build speed is great, but getting started and bootstrapping for them is also a real problem. So they identified build, we solved build, we made it so they didn't have to build and they didn't have to deploy because it just runs on their machine. And then they were like, well, I have all these upstream dependencies I want to use, and I want to consume these things. I need to set up an environment that's safe for me to work on these things. A new problem. Deploy bootstrapping. It's that part where you go, I can't just let you use prod all the time. You have to have their own place where your own dev services are running. So the attempt number one we came up with was do the obvious. Use minicube or run on your local machine. You could just take the manifests that we already have for all the Kubernetes stuff we've been building and apply them. And it should just all work out. Everything should be great if you do it that way, right? That's the common wisdom. But outcome, minicube is fragile and tends to break in mysterious ways. And I don't mean to be dumping on the minicube authors at all right now, but I can name 3 failure modes, at least right off the top of my head, around VM networking clashing with the host networking and getting a go panic that just tells you nothing what to do. You have macOS VM issues. And then there is my virtualization isn't set up on my developer's machine, and minicube doesn't tell me anything useful about that. And so they come over to me and look at me and go, what's wrong? And I go, I don't know, minikube is just failing to start. Not great. If you're like us, also, your deployment logic is probably not perfect. In a perfect world, everything in Kubernetes works on basically a loop. Retry until everything is up. In the way people tend to build software, they tend to assume they can have control over dependencies, especially if you're porting things from perhaps a pre-Kubernetes world. So there is a chain of events that has to occur. That often gets captured either in documentation, other tools that have to run, or it just makes assumptions about a CI environment with well-configured tools. The stuff that was running on CI was different from the stuff that was on developers' machines. So they didn't have the same, deployment pipeline that our CI stuff would have. Which all this really ends up happening is your developers look at you, they go, okay, well, this isn't working, and I need to get my work job done. Help me. And you kind of look at them and go, I don't know why it's broken. I don't know what to do because minikube isn't working. So you kind of go, that's bad. So my entire conclusion about minikube is it's for unicorns. If you have an application which is stateless, small, doesn't have many upstream dependencies, minikube is great for you. I don't know how many of you are in the room who have these kind of unicorn applications, but I'm going to assume it's a very small amount of us. For the rest of us, we actually need remote shared environments. If you already have any cloud services or any backend services somewhere, you likely already have a deployment pipeline to get that stuff running in production. That's great, because it actually means you can reuse that. And once you can give your developers the ability to get access to Kubernetes clusters on demand, you can just take those two things together and glue them together. And then you can have developers using their own Kubernetes clusters with the same deployment tooling that you have. So you can just leverage what you already have built. I'm sure anyone in this room is deploying stuff, you've already built stuff to do this. So our attempt number 2 was actually along this vein. We came up with this tool called KuberNot. It's a tool that allows you to get a remote Kubernetes cluster in under 5 seconds. It does it by actually running the Kubernetes clusters already. So there's no actual spin up time. We're not waiting for new compute instances to spin up. We're not waiting for nodes to join the masters. They're up and running. And developers basically set exclusive locks on clusters. They say, I want a cluster for X number of minutes with a name, and it hands them back a kube config with that thing, and then they can release that kube config at the very end, or it'll just automatically expire out of existence if they don't forget to do it. It's pluggable to support a range of cluster configs and backends. This is actually really important for us because we're tool developers. We build products, not services. We needed a way for people to get a range of environments to work on. So if you can think about where our stuff runs, Ambassador, which is our API gateway, runs on Azure, Amazon, Google, bare metal, anything you can think of. It can be run on a system that has any number of CNI or CRI configurations. It can be run on different operating systems at different versions of Kubernetes. You realize your test matrix suddenly becomes massive, or your reproducer matrix for a bug becomes massive. You can't have developers waiting for minutes to spin up Kubernetes clusters to do that. So we were like, well, we need to solve that problem. So we came up with this KuberNot system which allows them to just grab these clusters that are already running. Good news for this is going to go open source in 2019. It's currently not even available really to the public, but the entire thing will be available. I'll probably be announcing it on Twitter if you follow me. You'll see an announcement sometime in 2019 about that. Super excited because it's actually one of the first things I'll be releasing myself to the public. So CooperNotClaim is really where developers start now at Datawire. They start out with the CooperNotClaim, and then they kind of start writing code, or they do a Telepresence start and then write code. The order of these doesn't matter so much, but the idea is they get their own machine, their code is on their local machine, they telepresence over to that. That KuberNot system can already have all the backend upstream services they're going to need running for them. And so their loop really becomes basically code, dev test, code, more code, dev test. They don't have to keep doing KuberNotClaim. They don't have to keep doing telepresence over and over and over. They just have to write code, check their code, write code, check their code. Now, dev testing, it's ugly, it's painful, it's really difficult without shared remote infrastructure. And we kind of have a recommended way of doing it. The way we do it at Datawire is we set up nested API gateways. So what we would consider our production cluster has one API gateway running on it, and developers can talk right to that production API gateway. They can configure that production API gateway to have routing rules that send their connections over to their development clusters. And so they can leverage both a situation where they have to talk to the production services or their development services and back to production services, as well as their stuff that's running on their laptop using Telepresence. And it really helps to just have an API gateway that needs to be self-service. Once you have this, your developers just opens up a whole new world to how they're going to basically build software. They don't have to find someone and ask them to add new routing rules for them. They can just do it themselves. So we have code. We have build and deploy. Build and deploy is really claim the cluster, start telepresence, write more code. We have customizable dev routing. And then we have dev test. If you kind of think about this, to describe that topology a little bit more, it's internet traffic goes to the load balancer. That load balancer delivers traffic right to Ambassador. Ambassador talks to, if it's in a production stuff, goes to foo service, bar service. But there's that link. That link allows you to send traffic from the production service over to their development service. And they can talk to their developer foo service, their bar service. If they need to talk back to the stuff that's running in prod, they can do that. They might also go to another cluster if they need to. You can think of kind of an endless number of topologies you can come up with here. Also, I will say that the dev kube cluster, it does not have to be, if you don't want to, it doesn't have to be a physical cluster. It could be a namespace. You could have multiple ambassadors running inside of your system. So if you wanted to have a situation where you had basically virtual clusters in the form of just developers having their own isolated namespace, you could set up a per namespace ambassador and then have that routed. And then you could telepresence and have them set up so they can just telepresence into that namespace. So this is kind of how this works for me. When I work on this kind of stuff from time to time, I set it up. I have a host, basically a HTTP routing rule. I just say, if my name on a HTTP header is dev equals Phil, send it over to me. And goes into my ambassador. That routes to whatever I expected it to route to. Now, in this kind of situation, what I often do is then have bar service is linked to my computer with a telepresence proxy. And so I can have traffic coming in through prod cluster over to my developer cluster, and then that stuff can end up right on my laptop where I can basically debug it or continue to hack on it. So that's where we are today. There is still plenty of work for us to continue to do. Devs are way more productive than when we started. There's basically minimal waiting for them left in this workflow. Most of the issues we have now are around UX and making things more pleasant, easier to debug when they fail, making it easier so they have less commands to have to think about. But we're going to keep evolving this. The company has found it's basically increased productivity massively. Right now it works really well for 8 developers, but we're going to be scaling up, 20 developers hopefully by the end of next year, if not more. You want to have the ability to scale this as the engineering org grows. And we believe this will actually work and will be really productive for the entire company. So really my final takeaways here. Rome was not built in a day. It's a famous saying. You cannot start tackling this problem by basically going, I'm going to throw all the same technology at it that Phil did and build out what he has right tomorrow, starting tomorrow. Like, it just won't be possible. Actually talk to your developers. Figure out where your pain points are. Maybe it is deploy that is actually your pain point. Maybe it's not build. And then start there. And find the little pieces that you need to fix first and keep working on those. Just fix the right problems. And so there's a really big piece here that I can't actually explain how to do. It's communicating with your team and understanding how to gather the right requirements. And then figuring out a way to basically suss those requirements down to something that's actually useful and that you can iterate on. Just keep repeating this over and over. It's itself another dev loop. Dev tooling people, we all just work on basically fixing the problems as we see them. We're kind of like, digital plumbers in some ways. And I want to say this right now. I think a lot of people will kind of not heed my advice around remote clusters and will continue to use minicube or try to run kubeadm. You're going to have to do it at some point. At some point, you're not going to be able to run all your services on your local machine, or you're going to have developers basically coming to you going, how do I get more capacity? Can I get a laptop with 64 gigabytes of memory? Maybe, you might. It's cheap these days, I guess. But at some point, you're also going to want to have data storage requirements. You may have data storage requirements around GDPR. You may have data storage requirements, just huge databases you can't actually give your developers for whatever reason. Consider using remote clusters from day one and investing in that. Anyways, thank you everyone for coming. I will be at the Datawire I/O booth downstairs. Please come and chat with me. I am super friendly. I super love to talk to people. Check out Ambassador and Telepresence. They're both open source projects. Telepresence is a CNCF project as well. And tweet me at the Big Lombowski. I would love to get some feedback on this talk. I think we have time for Q&A. I think this clocked in at just under 30. Thanks. I don't know if,
so the question about Kubernetes, you said that you have a couple of clusters, right?
yes.
Once you have released the law, how do you reset the cluster? How do you make sure that there are no side effects left after the previous?
We terminate it. So these clusters usually run in Amazon or Google as an auto-scaling group. And oh, sorry, the question was, so he asked once a developer using Kubernetes basically discards a cluster, what happens? How do you reset it back to the base way it was? And the answer is, it's actually running in an auto-scaling group, so you just put a bullet in its head, and the auto-scaling groups in Amazon will bring a brand new one up to replace it. There's a follow-up question to that one would also be, how do you keep these things cheap? So you're probably going, well, that's a lot of money to spend on persistently running Kubernetes clusters that no one is using. You can do it with spot instances and preemptible VMs. That'll save a lot of money. But also just kind of balance the equation as developer time versus money spent on infrastructure. Anyone else? Over there.
This seems like a really great idea. Yeah, I would say for news websites or something along those lines, but on e-commerce where you have Sarbanes-Oxley and GDPR and all these other requirements where you should not have access to that kind of financial data. It seems like this is a great proof of concept, but there would have to be a lot of additional restrictions that I don't think that we would be able to use with this Telepresence.io. What are your thoughts on that, given where things are going and given the small set of developers you have so far?
Yeah, so unfortunately, I don't have a lot of experience with GDPR or doing this kind of compliance stuff. I could totally see that being a problem. I don't have a great solution. On the other hand, if you want to come by the Datawire IO booth and talk about that, I'm sure we can think of something, maybe where this would fit in. I could see a situation where you might run a not quite production cluster. So you have production, but you keep that totally isolated. But you basically have a replica of that as staging. And that may have sensitive data stripped databases that developers can use. Maybe that's a solution. Yes? Like traffic shadowing? Yes, yes, I can. Actually, I do that right now. I have a service where I basically use traffic shadowing extensively. So if you want to talk about that, also come by the Datawire booth and I can give more details about it. Yes?
If you have sidecar containers helping your main container, does Telepresence still work?
If you have sidecar containers, not yet, but we are working on a new version of Telepresence where that should be possible. Anyone else? Oh, yep.
I have to support a lot of Windows developers. Is there any support for Windows or?
There is not. So I'm so sorry. If you come by our booth, talk to us, we may be able to, we'd love to hear about it, okay? You're not the first person to ask for Windows support, so I think it's mostly a matter of, we need to understand how many people actually want Windows support. And is it do you have legacy Windows? Is it Windows 7 or is it Windows 10 with WSL under the hood? But yeah, come by the Datawire IO booth and I will be happy to talk about it some more. Anyone else? Going once, going twice, gone.